Okay, sir. I am starting the recording then.
Okay. So you want me to? So can you see my screen?
Yes, yes.
Okay.
Okay, sir.
Good.
I am starting the recording. Hello, everyone. I am Jivan. I welcome you
Okay.
all to this webinar on non-conservative optical action,
So you want me to?
organized by the OPTICA student chapter of ISO Kolkata. It's a great pleasure to have Professor Aristide Dogariu from University of Central Florida with us for delivering this talk. Before I go on to request my colleague Niladri Modak to
So can you
formally
see my
introduce
screen?
Professor Dogariu, few announcements.
Yes, yes.
Okay.
Good news
Okay,
for
sir.
anyone who
I am
wants to join
starting the
the
recording. Hello,
OPTICA,
everyone.
formerly known as the
I am
OSA
Jivan.
student
I
chapter.
welcome you
Okay.
There
all
is
to
a
this webinar on non-conservative
discount
optical action.
offer actually
So you want me
available,
to?
Organized by the
discount
OPTICA
on
student
the
chapter of ISO
joining
Kolkata.
membership fee.
It's a
So
great
you can
pleasure
grab
to
this
have Professor
opportunity.
Aristide
If you need
Dogariu.
any assistance, feel free to reach to us. You can email us or you can talk to any of the student representative. And also, I request the audience, anyone who is joining this presentation through Gmeet, or we are also going on live on YouTube. You hold your question till the very end of the talk if it is not absolute necessary. We are going to have a question answer section at the end of this presentation. You can also put your questions on the chat box or on the YouTube also. We will convey this to Professor Dogariu at the very end. So with that, Niladri, you can please go ahead.
Thank you, Jivan. Am I audible?
Yes, 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 you are audible.
Okay. So before we move on to the talk, I would like to introduce our speaker to the audience. So Professor Aristide Dogariu completed his doctorate from University of Hokkaido and is currently a professor at the University of Central Florida. Within the university, he is a faculty at Creole, the College of Optics and Photonics. Professor Dogariu is a renowned scientist in the field of optics and is a fellow of American Physical Society as well as the OSA, which is now called OPTICA. So he is also the recipient of the prestigious G.G. Stokes Award. So now, without further ado, I hand over to Professor Dogariu. Please, sir.
Thank you. Thank you for the introduction, and I'm really happy to be virtually there with with you, and I hope this small mishap with the timing won't bother you so much. It's no problem for me, but it's for you. It's getting probably late, so I will try to entertain you as much as as well as I can. All right, so we're gonna review today here things about how light induces mechanical action. Some things that might be very familiar, some things that might be obvious, some things that could be new for you, I hope. So light can introduce mechanical action in different ways. We know that plants, animals of different sizes, they do respond to light by bending, swimming, flying, but light can do even more for us, and you know, there's a lot of interest into transferring energy through light, and then transform it into some sort of mechanical, thermal energy. There are many applications that rely on this. So this is not the kind of mechanical action that we will discuss. The kind of mechanical action that we discuss has been known also for a very long time, and probably this was the first observation, the dust tail of the comets, and being very well known to Maxwell, trying to describe it. So this is just a few points in the history of mechanical action of light through direct momentum transfer. So without any kind of intermediate energy transformation. This is direct momentum transfer from light field.
Professor Dogariu, sorry to interrupt you. I guess you haven't shared your screen, entire screen. So we are not seeing your slides properly.
So you
need to share your entire screen rather than selecting just a PowerPoint.
Is this better?
No, you need to stop presenting, then again share your screen, select entire screen.
Stop sharing. Sorry for that. So your entire screen, not a window.
Exactly.
This is what you mean?
Yes, you need to screen. No.
So do you see my screen now or not?
You can see your desktop.
Yes.
Yes, it is visible.
You see it now?
Yes.
Screen?
Yes.
Okay. You see the screen, not the this split screen that I have, right?
Perfect.
Perfect. It is perfect now. Yeah.
Okay. All right. So let's move on. All right. So there are many proposals. Some realized already, some not yet. There are actually even as we speak, NASA-based missions that rely on this radiation pressure for propulsion. But practically, the real use of this kind of momentum transfer-based optical action relates intimately to the use of lasers for having directional sources and intense sources and so on. And of course, everybody's familiar, I hope, with this kind of a transfer of momentum in optical trapping. I will not, I just put them here to give you a flavor about the type of applications that rely on this. Cavity, optomechanics, optical forces, sources and intense sources, and so on. In the context of scanning probe microscopes, a lot of laser cooling in different modalities. They all rely on momentum transfer from electromagnetic fields. There is a long history of science in this context. Even more modern type of applications, ranging from different sorts of manipulations and microscopic scales to microfluidics and micromachining. In biology, these forces have found a lot of applications in uncovering basic phenomena, fundamental phenomena that actually induce tiny forces that could be measured quantitatively with these optical trapping tools. But the point that I want to make is that everything, and I really is there to me, this want to emphasize that everything started with this levitation trap invented by Art Ashkin, and yeah, this is an interesting quote here. I think that I fully agree that basic science is always well recognized. Well, it smells like something good immediately, right? It is a bit more difficult when these milestones really happen at the between disciplines, when they involve people with different specializations. Then it takes a lot of time to actually recognize the importance and the broad spectrum of applications that could rely on these phenomena. So yes, this is how all started. I'm just gonna give you a very quick and brief review of microscopic description of these forces. I'm not gonna stay on any of these, but I just want to make sure that for everything that is going to follow, we are on the same page by recognizing that matter modifies the way the light flows through, well described through these Maxwell's equations, but so matter modifies the flow of light, and light exerts forces on matter. This is the way actually a dipole with the polarizability P is actually affected by the electromagnetic field falling on it. And the basic of this interaction is very well framed in by Gordon in this very important paper. The way we describe this usually is in the context of Maxwell's stress tensor that intervenes in describing the time averaged value of the overall and the momentum conservation. These are basic things. The nature of this force can be easily captured by using a dipole as an example. You know, we can make out of dipoles objects of different sizes and so on. What is to be realized here is a small subtlety that actually even a dipole has actually an imaginary part of the polarizability, even if the absorption is not present, right? So it's this radiative damping that any dipole actually manifests, which becomes critical when we are describing the average force on the dipole and dividing it into real and imaginary parts of the polarizability. So even we don't have absorption, this part of force exists because of the radiative damping. This is what the take-home message is. There are different ways of describing this force. Familiar with the gradient force, that is the gradient of intensity. There is a pressure, radiation pressure. This was the first mechanical effect that was observed practically, but there is something more subtle. It's a spin or curve force type of thing that appears just because of the way the phase of the field is practically structured. This may come as a surprise, probably, but if you do the math carefully, you will see that this is always actually present, and it's pretty much similar magnitudes with this. Another way to describe it is nothing else but just reshuffling these elements into an intensity-based and a spin-based, right? This is the Poynting vector, and the spin term, that is essentially the time average density of this quantity. Another way to frame it, this is just a simple exercise in electrodynamics. You just you play a little bit with the Jackson-based type of electrodynamics, and you can write this force in different ways, which is interesting because it actually allows you to understand what is behind. So, yet another way to describe this force is into a conservative terms, right? A potential. This is what where this gradient force is actually coming from. and non-conservative terms that rely on gradients of phase practically, right? So these are the kind of terms that I'm gonna emphasize more in what follows. So coming back to the conservation laws, we have conservation of energy. We will not talk about this today. We have conservation of linear momentum and conservation of angular momentum. This is the kind of things that we will discuss. So we will start with conservation of angular momentum, of linear momentum. I'm sorry. The applications that follow from this conservation law is refraction, radiation pressure, and I'm going to show you something about some kind of a funny type of forces. So let's see. Linear momentum transfer. Light comes, light is scattered. If you do the arithmetic of the longitudinal momentum here, you will see that practically the momentum is decreased. Therefore, there is a force that pushes the object, right? This is what is called radiation pressure. Now let's imagine that we have a funny momentum converter. So you have a momentum converter that practically amplifies, magnifies the value of the momentum along the propagation direction. So what happens then? Because of the conservation, the force on the object, the reaction, should be negative. Is this something that is real, or is some really there are many momentum converters. A lens is a momentum converter, and there are many situations in which practically the scattering from microscopic objects is enhanced in the forward direction. That means that the reaction force on the object is practically negative. I'm going to describe to you one here. So let's suppose you have this complicated object. The scattering from here is described in a polar diagram. So if the scattering is more or less isotropic, like I said before, this thing is really pushing forward. However, whoops, for some reason. However, if the wavefront here is optimized such that the scattering in the center is enhanced, it can happen that if the wavefront matches the randomness of the scattering object, the light is scattered mostly forward, like it's shown here. Then, as a result of this linear momentum conservation, the reaction on the object becomes negative. So the force on the object is practically negative. Another interesting situation is that when you have an object that sits at an interface between two dielectric media with different refractive indices, the actual value of the momentum is increased if this refractive index, the bluish one here, is practically larger. So there is an increase in momentum. Yes, it is a change in the direction of the momentum, but also an increase in its value along this interface. Of course, this is in the picture of Minkowski's description of the momentum. So we have a practical momentum amplification. If the momentum increases for the light, the action on the particle should be opposite, right? So there's another situation where a negative force, momentum of light in this to the right, the force, the action on the particle to the left, right? And yeah, this is a you see in this animation, these are particles that actually sit on the surface of the air water, at the surface of the air water interface. The radiation is directed along where of this arrow, but the movement of the particles, as you can clearly see here, is directed backwards. So this is a demonstration of a negative action of light that relies on this momentum amplification. It's even better seen here in the plot of the average velocities. Yeah. So this new mechanisms for manipulating particles back and forth, and so they attracted a lot of attention, and we have used it in looking for different phenomena at larger scales, as I will show you a little bit later. All right, so moving on to a conservation of forces that rely on conservation of angular momentum. We know that we use it, this fluxes of orbital and spin angular momenta, very easily to define them in paraxial situations. Not so easy, like Michael Berry pointed out some time back. Not so easy for non-paraxial fields, but in most of the situations that are of practical interest and easier to access, this kind of a decomposition is acceptable. And as a result, at the interfaces between two dielectric media, we have a lot of the field, the electromagnetic field, that can be interpreted as a, for instance, as a spin Hall effect for light, in which practically by analogy, this spin orbit coupling, the accumulation of this phase in here is in analogy to the actual magnetic field, right? To the real spin Hall effect. So the analogy is magnetic field analogous to gradient of refractive index. As a result, you have accumulations in. You start with mixed states. You have accumulation of pure states through this effect that is relying on the refractive index mismatches. So this happens actually not only for a well-defined waveform, a beam. It's certainly present also for a plane wave or in a spherical geometry. So there are currents, but no net fluxes because of this infinite geometry, or this infinitely wrapped geometry in a circular refractive gradient, refractive index gradient, this geometry. So the question that we were trying to answer some time back is that certainly there is a broken symmetry when the object is finite. Is there any effect of that, consequence of that? The consequence is actually, I would call it very simple, almost trivial. You know that in scattering from well-defined entities, the spin coupling, the orbit spin coupling of the angular momentum is something that is very well understood. In any direction, the ratio between the total angular momentum flux density and the intensity is a constant. So if I have a scattering of a, like in this animation here, I have a circularly polarized light, at 90 degrees, for instance, I have perfectly linearly polarized. That's exactly a consequence of this spin orbit coupling. So, can this thing be observed? What is the consequence of this thing? Well, if you have here, for instance, right, this is your scattering, this is your rotating dipole, if you wish, and you observe it from far away, you will have a virtual location of this object, which is not coinciding with the real physical location. If you change the handedness, you have the opposite phenomenon. If the radiation from the dipole is linearly, if the dipole it's a linear dipole oscillating, then you would have this location right there, right? So that's practically how a scattering from a sphere is supposed to redistribute the radiation, and the location, the apparent location of this source is a function of the size of the object, and certainly it can have values that are really comparable to the size of the object. So this is not a tiny effect. So you have a circular object of 2 microns, and you have a very large deviation in its perceived position. Right. This is another illustration of that. When the object becomes even larger compared to the wavelength, then it becomes a little bit more complicated. But there's no problem. From the far field, when you look from the far field, you see that the radiation practically does not originate in here. It originates somewhere in a displaced position. Can this be measured? Of course, it can be measured by doing a scan across particles, spheres that have been excited with left circularly, right circularly, and linearly polarized. And practically, you will have these shifts that are visible, can be measured with a scanning machine, and practically what you have a demonstration of a spin-hole effect in a spherical geometry. Very simple experiment that actually mimics almost perfectly the spin-hole that is observed for electrons. Again, the role of the magnetic field here is played by the gradient of refractive index that around this sphere. Now, is there any mechanical consequence? Because this is what we're talking about. Well, you can take again that sensor of the phase, which is that dipole, and just try to go through a field like this or like that, and accumulate the phase, calculate the electromagnetic force around, and you will see that practically around this vortex there is a force accumulation, and therefore a phase accumulation, and therefore that third term in the force that I mentioned before, it starts to appear. Let me explain to you exactly actually how the experiment works. Okay, so I have scattering from circularly polarized light. I have plane wave, a right-handedness from the bottom. The radiation scattered from here circulates, like I said before. At the same time, I have a linearly polarized light with the polarization vector in plane. You overlap them, right? So you excite the particle with 2 perpendicular plane waves, one circularly polarized, one linearly polarized. They will have radiation pressure from both plane waves. The particles will essentially be pushed in both directions, but because of this interference between them, they will have another component of the force that is due to that circulation of the phase around. Practically, you will observe a deviation of the particle that is transversal to the plane that contains the two-wave vectors that eliminates it. Right? So is this apparent position of the particle that produces, you see, an interference that is essentially shifted to the right, to the left. So if I have a consequence, if the field is modified, the scattered field is modified through this spin-orbit coupling, then the action on the mechanical counterpart should also reflect that. Like I said, light is modified by the interaction, but also light imposes, as a result, imposes a mechanical action on the particles. So we did this experiment actually with two beams with the appropriate circularly polarized and linearly polarized, orthogonal at the surface. We practically examine how particles at the surface are pushed practically transversally, right, or in plane in this location. But the funny thing is that this interpretation that I just described to you, you see, so this is the circularly polarized emitter. This is the linearly polarized emitter. This is the circularly polarized one. This is the linearly polarized one. The interference is this traditional shift and I wanted to actually put this picture in here because I want to put this other one underneath. This is equivalent, similar to what you have in the Aharonov bomb setting, in which this magnetic field is played. The role of this magnetic field is played by this circularity, and then the interference is practically modified because the accumulation of this phase. It's a similar description to what we have in this mechanical action. There is more to it. The force on a dipole at this interface can be calculated on a dipole. This is just a simple exercise, but on a larger dipole here, on a larger object at the interface, there is a non-trivial force. The field is non-symmetric. The object placed at the interface between two dielectric interfaces modifies the field, and therefore there is a force component that is different. And these are detectable forces. These are large forces, and to actually see them even better, we played an even better trick. We practically amplified their velocity by confining them into a string at the interface. You see here how in time they move to the right, to the left, depending upon how the handedness of the circular component is practically changed. All right, so I'll end up with this section by saying that non-conservative action of light can be created by on surface-bound particles in different ways. So you can have radiation pressure. You can have that kind of a negative force that I told you due to the momentum amplification. You can also have lateral forces, like I described lately, because of this action of the circularly polarized light, and this spin coupling, orbit spin coupling that happens at the interface. So practically, non-conservative action can be pointed forward, backward, sideward by playing with the environment in which these effects are observed. Situations where on electromagnetic fields that were very clean situations, right? We could describe them as plain waves. There was no wavefront modification other than as a result of the interaction. So objects there were really under plane wave excitation, let's put it simply. But there is a lot of possibilities that are brought in by actually complicating the fields, right? Many way of structuring the light leads to different modalities of trapping, counter-propagating waves. You can create a optical conveyor belt, right? By modifying the phase, the interferences move right, back, whatever you want, right? You actually can move the particles back and forth. You can use structured illumination of this nature, right? And then particles that are actually trapped in this circular potential, and the action of the angular momentum creates this perpetuum motion on particles that actually have a little bit of an imaginary part on the polarizability. You can do even more. You can actually spin particles in these locations, and so on and so forth. You can interfere beams like this. Like I said here, you can take these non-diffractive Bessel beams that are in a paraxial approximation, and you interfere two beams with a little bit different component of momentum along Z, and let's see what happens. So these rotational scale invariant, how they're called, this is what happens in a cross section, and you will see that practically the action on a particle like that actually is located in one of these interference is such that, I don't know why this animation is not playing very well, but the fact is that the particle spirals backwards in this rotating fields. There are other type of complex fields that actually are generated by more interacting particles. So you have, for instance, a pair of particles excited by a common field create a bound state. We could call that an optical dimer, right? Radiation from this particle pushes this particle away. On the other hand, radiation that is scattered from this particle decays away from the particle. That creates an intensity gradient that actually pulls this particle in. And at some preferred distances, these two counter effects balance, and they are becoming bound. This is what the optical binding is. So when this matter wave coupling is practically symmetric, of course we have an action and reaction law, right? This particle pulls or pushes as much as this one pulls or pushes this other one, right? So this when the system is perfectly balanced, there is no symmetry broken, and so then this principle of action and reaction works pretty nicely. So now let's see if we look a little bit different, how these particles actually talk to each other. So let's suppose that I have two particles. Let's put this thing on. Let's suppose I have two particles, but they're not identical. They're not identical. They have two different type of polarizabilities. Then all of a sudden you will see that practically, this is a calculation for silver and gold, for instance. Now you will see that the field acting on a dipole, on each of them, they will be different because of the different values of the of this, right? So even though in fact there's nothing wrong when we realize that practically this system, it's an open system. Being an open system, we should not expect the third law to be valid, right? That's a subtlety that in this business is rather critical. So the scattering of this from this dimer, it's asymmetric because of the different properties, right? So even though these are actually the forces could be equal, it means that there is a force on the center of mass of these that can be to the right or to the left, depending on the optical properties. So the force on the center of mass, it's a lateral force, even though, right? And you know, the particles can have equal forces, right? But they can be negative or positive, but non-zero, right? That's the idea. So the entire dimer can move to the right, can move to the left. Minor, of course, there could be other situations where the forces are equal and so, but they are not really stable, right? So in this condition, right, if a force is like that, the particle located here will have the tendency to fall down. And here it's almost close to a minimum, so this is a stable position. So for this situation, the dimer is expected to move laterally to the right. Okay. Real objects are not dipoles, right? Real objects are complicated, made of many dipoles. So we need to have a more involved calculation if we want to determine the net effects on bigger objects. Now, this is just a quick question on electrodynamics of rods and bound spheres. So what happens if I excite these objects with linearly polarized light along this direction that I'm moving my pointer here? So will they align along that direction or not? Well, turns out that the rod, yes, indeed, aligns along the direction of the polarization, while the optical bound particles orthogonally. Why? Well, if you do a little bit of the math, you will see that practically the systems try to minimize their energy, right? And the potential energy induced in this situation and in these other situations are different, because the little dipoles that are included here, they really interact through near fields that have this shape, while dipoles in the two spheres here, they will interact among themselves with far fields, which have this shape. And this is the reason, actually, the microscopic reason why these two objects, they can have the same mass. They could have they macroscopically, you could say that they have the same type of symmetries, but they really react differently to the electromagnetic field, right? So based on this, you can do a evaluation of the role of the interaction between the dipoles in the polarized electromagnetic field. So this is a pair of coupled objects that are excited along this direction with linearly polarized light. They will actually have the tendency to, I don't know why my computer just froze. I'm sorry for this. I will have to do something. Can you see my screen now?
No, it's not coming as yet.
You can see your desktop, but not your presentation.
I'm sorry for this. Can you see it now?
Yeah,
You
yeah,
can see
yeah. Sure.
Yeah. So this is what will happen, because the objects are large. The distribution of the forces inside the object is not uniform. Therefore, as a group, they will try to rotate depending upon how you align the linear polarization, but they will also spin because of this torque that is induced in here. If you excite them with circularly polarized light, the situation it's even more interesting. I would just go to this. So they will have a continuous orbital action, orbital trajectory here, but they will also spin along their own axis. It's a very curious rotation that spin and orbital torques practically, right? And these are completely lossless objects. There is no imaginary parts on these dipoles other than on the dipoles that are the constituents of these objects, other than those radiative components that I mentioned before. So okay, and this is the last part, putting them practically all together. So we have now complex systems. This is coming closer to real life. We have complex systems. They are subject to thermal fluctuations, external influences. These external influences can be thermal, can be some sort of fields or whatever. The response of a complex system like this depends on the nature of the interaction between the elements. You would expect that the evolution of this internal structure will be very complex. You will have manifestations of non-equilibrium. You will have displays of collective motion of these things and all sorts of so-called anomalous phenomena. This is what is the realm of active matter. All of these interactions generate properties as a response to the external excitations. This is what happens with biological with the cellular motors. This is what happens in large populations of bacteria. This is what happens in chemical waves that propagate through networks of polymers, for instance, in all sorts of other situations. So at some point we really wanted to see if this kind of an active medium, complex action, can be generated by light in an all optical manner. So we constructed a colloidal system that scatters very strongly the light, and we created, putting this in a sort of a cavity, we practically created conditions in which the diffusion of the particles is strongly coupled to the diffusion of light, right? Changes in the positions of the particles change the distributions of these speckles, of this field. This is the random field this is the random force that is exerted on any particle by the electromagnetic field. As a result, the particle moves, the configuration of the electromagnetic field changes, the force changes, and so on and so forth. So this induces a very strong coupling between light and matter. How can we probe this? Well, we always, after simple things, we just probe this dynamically by looking at the fluctuations of the light, because, as I said, particles move, change the configuration of the field. Therefore, probing the configuration of the field, you indirectly probe this coupling, looking at the power spectral densities of this. So what you see is what you have here. The power spectrum of these kind of fluctuations is expected to be a -2, right, from the particle diffusion considerations. But as you start increasing the power, this light matter coupling is enhanced, and this the particles become super diffusive. They diffuse faster because they are under the action of much stronger gradients of all sorts. We cannot distinguish, unfortunately, in this thing, which part of the force is conservative, which is non-conservative, and so on and so forth. Not yet, at least. But the net effect is that the particles really become super diffusing because of the light. So practically, we have a system in which we could test phenomena that are really pertinent to big scale biological systems, and this is the type of things that we are practically aiming at with this model system. So you can do very basic physics, looking into the non-equilibrium thermodynamics of this movement. You can actually test the interesting occurrence of long-range electromagnetic interaction in between spheres of different separation distances. And we are pursuing now a number of applications in optical control of matter based on this strong coupling between light and matter in systems that, you see, this system is not really open, but is not closed either. So that is actually an experimental knob that could be used to adjust the level of these interactions. So to summarize what I try to survey today, right? Optical forces of non-conservative nature can be directed at dielectric interfaces in all directions at will. You can create forward, backward, lateral forces. In complex fields, you have even more flexibility. When the complex fields are created by the light source itself, by controlling the light source, or the complex fields are created by the interaction between the particles themselves, you have practically more flexibility in creating mechanical action that is allowing you to study phenomena at these mesoscopic scales with objects of micron size that actually otherwise you wouldn't be able to do it. I want to again emphasize that the difference between inducing optical action non-conservatively and conservatively, with laser trapping, which is the conservative part, right? You are limited in the sense of the consequences of motion that you can impose. Let me just go one here. You see, so this is the non-conservative part that we are actually addressing with these kind of machines that spin forever. You could look at non-stationary properties in small scale thermodynamics that you wouldn't be able to actually do it differently. If we would have more time, we could get into more details of that. But for the time being, yeah, I think that this is an exciting, at least for me, it's an exciting area of research, especially this dynamic coupling between light and matter, and the possibility to control the type of diffusion that happens in these complicated systems. And I cannot end without thanking all these guys and girls that practically did this work over the last few years. And this is it. Thank you for your patience and attention. All right.
Thank you, Professor Dogariu, for your wonderful talk. And the platform is now open for questions. Anyone has any question, please raise your hand and unmute yourself. Professor Nirmales, you can go ahead.
Hi, Professor Dogariu. Thank you for a really wonderful talk. So I have just one question about optical binding. So is there any, available formalism that deals optical binding beyond this dipole scattering? Like, for example, if we electric dipole, beyond that, like magnetic dipole scattering or other higher order modes?
So you're, if I understand correctly, Optical binding with when you're thinking about an analytical description of
Yeah.
optical binding in terms of high order modes.
Yes, yes.
That's right. So I'm not sure. I'm really not sure. For two dipoles, yes, we can have it's a very clear analytical solution. For larger size objects that would involve higher order modes,
Yeah.
we found that numerics is the way to go. Numerics is the way to go with this large scale Green's function between interacting dipoles.
Okay, so but so even then, say for example, if we are talking about, let's say, electric dipole, like if we are talking about the scattering A1 modes,
Yeah,
and then the B modes also, do they have similar kind of optical binding, or
they will have. I think that they will have. However, they will probably not overlap spatially. The binding location may not be the same.
okay. Yeah, thank you.
Mhm.
Yeah, Athira, please go.
Hello, Professor Dogariu. Thank you for an interesting talk. I have few doubts. Towards the end, you commented that for the optical binding, we cannot really comment that it is neither open system or nor closed system, but still you commented that it is a non-conservative thing.
Mhm.
Why do you state that it is neither closed system nor
No,
open system?
I was saying about this. This is a semi-closed system, if I can say that. The optical binding configuration, the optical binding, it's certainly an open system. In this configuration, light comes in and goes out continuously. Energy is pumped into the system continuously. So this is an open system.
Okay.
But
And
in here, like I said, we put this thing in a cavity. The cavity was not completely closed because we had to actually bring in light and measure the light. But yeah, more than 70% of the surface was practically reflecting. So this is a prototype of a semi-closed system, right? Mhm.
so in that case, can we call this as a non-conservative?
That is a very good question. This is why I hesitated to call it like that in this case. There are elements that are non-conservative here, but there are also elements which are highly conservative. So look at the speckle, for instance. Do you see my mouse?
We cannot see your screen. We can see only your desktop.
So, but you see this picture, right?
No.
No?
No, we cannot see your slides.
See the plate.
I'm sorry. Hang on a second. Now, can you see it now? Hello? Can
No,
you
we
see it now?
cannot. We
Okay.
cannot. You need to share your entire screen.
Okay. All right. So you see the speckle that I'm pointing at here, right? Now this speckle in here means that the intensity is practically changing across. There's an intensity gradient. The net effect of that intensity gradient is a conservative force that acts on any particle that would be around here. However, nothing precludes that there might be around here a phase circulation in this spectral field. I may have a gradient of phase in this complex field. Now, this gradient of phase will induce a non-conservative force on it. And because I have many of these speckles and many more particles around, it is very hard to say that the net effect is due to one or the other. There are all of them together.
So you are considering it to be a local kind of non-conservative effect.
Correct. Locally here, there could be no problem with that, of course. But in this context, in which you have so many particles that change the field so dramatically and dynamically, to try to separate into conservative and non-conservative at this location so might be very difficult, probably impossible.
Correct.
But for one single particle, and so there's no doubt, it can. It's a mixture.
Correct.
Yeah.
Thank you.
This is why, you know, there's a big. I mean, people argue about. This is why I wanted to give you 3 or maybe 4 ways in which an optical force can be written and decomposed on components. But you see, this decomposition on components, we're just making it for the sake of an explanation, actually. The force on the particle is only one. The force on the particle produces an effect, a velocity, an acceleration, or right, depending upon the type of movement. But that's it. The effect is only one.
So now on curiosity with the experimental side, the detection that you're making is from the backscattering mode, if I'm not wrong.
On this particular experiment, yeah.
Right. Okay.
Yeah.
Thank you.
Yeah. It's practically looking at the fluctuations of intensity.
So, is there any more questions? Yeah, Abhijit, please go ahead. Yeah, Abhijit, please go ahead.
Hello, am I audible?
Yeah. You're audible.
Thank you, Professor, for the talk. I actually want to discuss the non.
I can barely hear you. I don't know.
Hello.
Yes.
Hello. The non-conservative action comes due to the scattering force of the in optical trap, right? The scattering force part, right? Hello.
Abhijit, can you type your question?
Hello.
Abhijit, can you type your question?
Yeah.
Can I see the question somehow? What should I do?
The question is whether catching.
Professor Banerjee, even your sound is breaking. Maybe you can type your question.
So I think, can I repeat what I could understood? Sorry, that perhaps the question was that the origin of the non-conservative force, was it the scattering force? Professor Dogariu, I think the question, can you hear me?
Yeah.
Yeah, I
So
think the question was probably what was the origin of this non-conservative force? Is it the scattering force?
by scattering force, we mean,
I think by scattering force, they mean by just the radiation force. I mean, sorry, yeah, the scattered light.
yes, yes. Then the answer is yes.
Mhm.
Yeah. So
Yeah, I think because this is
everything that is not due to an intensity gradient,
right.
we can call that scattering force. That's absolutely correct. Yeah.
Yeah.
It can be just simply the a pointing vector
Yeah, I think it's
contribution. It can also be
calculation.
a spin contribution, if you want, a curve force. Yeah. But everything that is not due to a gradient of intensity, we could call that scattering. Right. Yeah. And in laser trapping, that is a nuisance, right? Because people want to trap the particle and hold it in a position that they want, right? But because of this radiation pressure, that will be a little bit offset
Right.
with respect to the
Yeah, thank you.
Okay.
So am I audible actually?
Yes, sir. Yes, sir.
Yes, yes.
Yeah, there was probably a network thing because I could hear a wonderful talk. So I just wanted to ask you. So one of the very, very important consequences of spin-orbit interaction is the generation of a transverse spin, right? Because of the longitudinal component of the electric field, you basically have a transverse momentum. It gives you a transverse spin. So are you sort of aware of, and things which we call the photonic wheel, I guess. So are you sort of familiar with experiments that have sort of demonstrated the existence of this photonic wheels like phenomena in say optical tweezers or other stuff?
Yeah, it's an interesting question, right? No, so that the short answer is no. I'm not aware of an experimental demonstration of a demonstration of a mechanical consequence of that. But I wonder if,
That won't be theoretical, is it? It's just the theoretical, numerical. Maybe some studies have been done. So no experimental demonstration is yet in any sort of thing, right?
as far as I know, I don't know. I'm not aware of that. But that will actually lead to one of these unusual directions of optical action, right?
Right.
It will, yeah, it will be something that actually moves the object away from the main K vector,
Yeah.
so to speak.
So one of the big challenges of observing this in optical traps would be that this would sort of the imaging, because it moves in the direction of the beam.
Yeah.
Right. So particles would actually. So yeah, that itself is a very difficult thing.
But
Maybe.
I have just a comment to make in this context.
Yeah.
So I think that your that classic paper, where you experimentally showed that this from this scattering particles, that you could map the scattered energy distribution for two different circular progression, that itself also will be dependent on the longitudinal component. Right? That separation is purely due to the near field circulation.
Mm.
So that paper that you are referring.
Yeah, Nirmala, what Professor Dogariu I think implied, and what I also implied, was that mechanical action actually has probably not been demonstrated.
Yeah, no, but that field was mapped,
Right?
I think, in that paper, and
Yeah,
then
the field has been mapped. Yeah,
another paper, I think Professor Dogariu himself has on this on different OM, how the particle can distinguish different OM in terms of scattering also.
Yeah, if I don't know. Yeah, yeah, like you said, right? This would be essentially something that
Circulating, right?
tumbles
Yeah.
along the direction of light propagation, so to speak, right?
Yep.
You need to see some kind of a
Circulation
rotation.
field.
Yeah, yeah.
No,
Now,
it's going to be out of plane, directly out of plane of the imaging plane. Actually, that's the biggest challenge, I guess.
yes. Right, right. So you need probably, yeah, it's an interesting point. If we would know about the magnitude a little bit, probably, I can think about way of indirectly observing somehow.
Yeah, that is pretty. Yeah, that's nice. Yeah, some projection or something of that sort, or maybe see a reversal. So if you actually come in with right circular, then you get a left circular as well. But then the given sort of some sense of rotation getting changed or some gyroscopic motion, maybe that also could be.
Yes, some people had earlier used this some kind of those near field antennas to propagate in the far field and to look at that this longitudinal component.
Yeah.
And another thing was that you talked about super diffusive motion, but subdiffusive motion is also something that is very much studied in StatMech sort of experiments, with optical tweezers. So what kind of light field do you think would be useful for that? I mean, could you motivate such motion using some kind of specialized light fields, or would it depend on the on the particles or on the nature of the matter that you're actually investigating?
So you're right. Yeah. So subdiffusion, it's rather easy to observe, right? Because you're practically constraining the diffusion. That's what it means. So you actually push the brake, if you want, to the particle diffusion. So any kind of conservative action of that nature would create a subdiffusive regime. People in laser trapping, when the traps are not so tight, then the motion of the particles is more or less subdiffusive.
Yeah.
The more, right.
Just the Gaussian beam itself, but a very loose trap, you basically get some stuff like that.
Yeah, exactly.
But then one thing would be that if can you get a sort of transition from, I don't know if people have done it, but it's if you just use a spatial light modulator or something, then can you see transitions from, say, subdiffusive to normal to super diffusive, something like, I don't know, maybe some phase transitions kind of stuff?
That's a very interesting question. Right. So actually, we do have an experiment like that right now. In which we do have a random field that we practically manipulate, we modulate spatially and temporally. So,
great. So have you actually published on this? Can you just then send us some papers or something? Because this is fascinating.
I will send you something there. Yeah.
Okay. You were saying something. I probably interrupted. Yeah, please go on.
No, I was just trying to say that the most complex motion involves a random walker, a particle, let's call it like that, right? That is placed into a external potential that changes in both time and space. So that's actually, it becomes very, very close to the most fundamental type of motion that you can have. Now, if we can manipulate them optically, a lot of things can be probed like this. The problem with these things is that the actual forces, the magnitude of them, it's rather small. The effects are small, and observing them quantitative and quantify the observable is not easy. That's the thing. But yes, you're right. You can create conditions in which the movement really transitions from you just imagine that you have a speckle field that is frozen, because of what we said before, the movement is more or less subdiffusive. And then you start transitioning from that situation to a situation in which the particles practically get kicks from all the dynamic speckles, so to speak. That would be a super diffusive situation. So you could, in principle, create that. But the question is, how do you observe it? That's the
maybe just the Brownian motion. You showed those Lorentz, those power spectral thing where you fit that Hurst exponent kind of stuff and see that probably could be an.
That's exactly how we try. That's the only, in my opinion, that is the only realistic way of actually measuring it, because first of all, you need to have an ensemble. The larger the ensemble, the better the information you get. So you need to look at many particles at the same time. You look at one, it's not.
Tap the particles and speckles, right? And then see how they evolve. And you sort of video microscopy or something you probably do.
Yeah.
Because I think detectors would make it very, very difficult. I mean, photodiodes or something like that would make it very tough.
Yeah.
Great. Fantastic. So I would really look forward to these papers. It's quite, so basically just the potential landscape you change and you can drive different types of domains.
Correct. Yeah.
If there is no further question, then let's thank Professor Dogariu once again for this wonderful talk, and we hope that after this pandemic, maybe we can visit here and give a virtual talk. So with that also, thank everyone for joining.
Thank you, Professor Dogariu.
Yeah, thanks a lot. And we would really, we from the Department of Physics, we would definitely, extend a very, very warm invitation for once travel gets normalized. I mean, we hold conferences, at least from the OSA chapter, the OPTICA chapter, and the SPI chapter. We have this yearly conference, but it has been stopped because of the pandemic. So we would really love to have you here. I mean, physical meetings are much better than such stuff, but of course,
Thanks a lot, Of course. Sure. It will be a pleasure. Right. Once we reach some kind of normality.
Right.
Yeah. Right now, I don't know what we're doing. It's either subdiffusive or super diffusive, but we're not doing normal things. So I don't know.
Zero diffusion, right? There is rest.
I don't know. Yeah. Mm-hmm. You're
optically bound.
Yeah.
Completely bound. Tightly bound.
Completely bound. Right.
We're all trapped, you can say, trapped by the virus. No diffusion at all.
Yeah. By the way, how are things at
things are improved slightly better, of course, now, and we'll have to see maybe another month or so.
Yeah, because the festival season is on, and so India, the problem, is the data is not very reliable. So you essentially go by, accounts of your own, small world. And if you see people are getting ill, then it's not very good. But of course, in France, it's like, I mean, UK is pretty bad. I think Europe is staring into another bad winter. Right?
I know.